Okay, so let's continue where we left off. Let's open our container project. We should have called it X containers from the get-go and not X string, since now it was extended to really all the typically useful container types. So let's see where we are. Solution X array is very incomplete, and xmap, xtable rather, which we made last time, is not quite as incomplete. So the remove functions were for home, for later. Right. We need to finish our insert function such that it can act on the different insert modes, and we should add an iterator to it. That would be, I think, quite a good addition. I think adding an iterator to the array was a homework. Was it? Or not? Let's see what homeworks that we have. Yeah. For list it was the homework, so for array it was already implemented, yes. So we will do it today for the table. After we finish the insert function. So let's do that first. This should not be that difficult, so we have already the get pointer function, which finds us a pointer. So we first see if there something is present in our table for that key, and then only if there is something present, we care for what we do next. So if it's present and mode is what did we had now replace, then we just return false, or else we return true. But first we will replace the data entry value. That's a what's our value defined? I think it's a normal value, it's not a pointer, right? So value is then just equals value, and that's it. So we just replace it, and our insert is complete. We have get all and the operator here. Okay, so I think the base functionality of the table is really implemented. We could in principle make it a bit more complicated by changing insert pointer to define whether we are inserting at the head of the linked list or at the bottom, but I think this is a rather special case, so we will not do that. If one would need this especially, then this could be added manually. What also would be good to have on the thing would be a search function, so that we can find entries providing a filter, but we can do this manually with the iterator as well. So let's first start with the iterator, and then we will see how far we come from there. Let's implement it before the table dump here. So as iterator, and let's think about how we want to implement this. So we will definitely need to know from which bucket we are retrieving the data. So int or size t bucket index. Then we will need to know which is the current entry we have retrieved. Since it's a linked list, we don't really have the ability to just use an index, so we will need a pointer. Bucket item starts at null for beginners, and depending on what we want our iterator to do, we need the ability to access other buckets. So we should get a pointer to the table element as well. That's our iterator here. I mean, either the table element as such or just the bucket array. We need the whole element because we need to be able to access bucket count, so it's easier to just have the whole thing. Table the internals we will do in a second. Now we will first look now first we will look into what other things we will need. So as you remember, we need a begin and an end function, which will give us a begin and an end iterator. But in maps, or generally in a container types where we have a key, it is customary to have at least also a find function, which takes a key. And for find there is no defined semantic, so the begin and the end, they need to be lowercase for this range loops to work, but find can be whatever we want. But let's keep with the STL notation and keep it lowercase. So our find takes a const k reference key and will return us an iterator pointing to the first occurrence of this key in our table, and then we can use the plus plus operator to go to the next and the next and the next entry, which adds another complication for iterator, since inside of the bucket the keys might be different. We could want to add here a key. The other option, of course, would be to only keep the key transient and always read it from the current bucket item. So this would work as well. So let's try maybe first with this approach. It's more memory efficient. Okay, so let's continue with our iterator. It will definitely need a constructor, and what we might want to is to make it such that a valid iterator cannot be constructed by anything else than our own object. So we'll make here somewhere a private, rather protected area where we will put the actual we will also need the destructor. So we will make a private area where we will put constructors that take all the parameters. Or what we also could do is we could define those parameters all as protected. That's maybe even better. And then we just construct it manually. We use this constructor and then assign these sub values. That's even more elegant. So let's do it this way. And since it's struct, it's public by default, so we don't need to make those to public manually. They are public by default. So we will need a copy constructor, obviously, as iterator reference other. And here we'll just use the next to be implemented assignment operator. As iterator reference operator is equals as iterator other Klammer auf Klammer zu. Now we just copy all those elements from the other. principle we would not need to make this explicit, since we really just make a automatic assignment. So the way the compiler would have implemented a default assignment operator would just do the same thing. But I think it's nice to have it explicitly, just that we see really what is going on, and we might want to change the mechanism in some way if we want. We could also, if we would hold a key here, might want to make this typo? No. Did we forgot? Oh yes, that's the reason. We ate a bracket and the whole thing got screwed up. Then of course we need the plus plus operator. Actually we could just copy it from our array implementation, just so that we don't forget anything. Suck. But we will of course delete the contents so that we have to redo everything. Right, so for the is equals and is not equals, we could actually here asterisk exclamation mark asterisk is equals other. Here we can reuse the other operator just by negating the result of what this operator returns, and here for them to be the same, of course. We can either make a large if, or we can make it step by step. This must be same, this must be same, and that must be same if or just return this is same and this is same and this, yeah, that's more elegant. So we just compare whether all the three values are the same, and then it's the same, and obviously so an explicit negation would be a bit more efficient in as far as that if one of them is not would it be marginal, it really doesn't matter, it's good enough to make it this way. Okay, let's think about the next steps. So in our begin, or maybe let's start with that. So we will need to be able to define an end iterator that somehow says that there is nothing more to iterate to, and a good start would be to just define that if bucket item is null, then the iterator is no longer valid, and then we have end. So E, and in this case we actually don't really need to do anything because everything is null already by default. So if we leave it at that, that would be as simple as it gets. And of course the begin will be a bit more complicated. So for the begin we will need to assign some of the values. So table is m, bucket index is 0, and bucket item would need to be initialized to the first entry, if there is a first entry. So we will need to have a check here. So if there is no m, or m bucket count is null, or actually rather if just uCount is null, then return end. Okay, but this will be challenging a bit because the first bucket might be empty, so we will need something to advance to the next bucket and the next bucket and the next bucket until we find something that is valid. So let's see, we have m, we have index starts at 0, so we don't need to start assigning this. Yeah, we will just go through all the buckets until we find something that is not null. So we had already a loop here that goes through all the buckets, I think. Can we use? I mean, it's we could go with that loop, or we have one that goes forward, one that goes forward. Buckets. Yeah, let's go with this one. Right, so we assigned M, we have our loop, we go through bucket count, and in principle we just want to find the first bucket which is not null. So if bucket count, sorry, if M buckets from I is not null, then we can break, and before we break we'll assign E. Bucket item is equals bucket item and bucket index ist gleich E, so that we know in which bucket, and we have the first bucket item from the list. Also, we could in principle, just for completeness, assign here M, such that if we would have an operator from a different list, that we could check whether they are compatible, because you might mistakenly take an operator for the wrong object, and then this would not work. So, and here we could add an asset if we would using assets, or something that throws an exception if actually tables are not the same. We do any comparison between completely invalid iterators. But for now, let's just leave it as is. So here we have the return end. Okay, so would that work? That seems right. And in the end, if this loop, if for some reason count is not 0, but this would end up false, which should not happen. But if it happens, what we end up with will be exactly the end iterator, since those two variables will not have been set. Good. Now what we also need is the increment operators. Alright, we did not deleted those. We need to add some functionality in here as well. And it would be expedient, I guess, to have a function that advances to the next iterator, so we don't need to have this twice. What we also could do is we could just use one operator to implement the other operator. Alt plus plus, sorry, plus plus alt. Yeah, so this operator will make a copy and invoke that operator and return the copy. So that's as good as having a dedicated function that which does the same thing. So here, when we are in the plus plus option, we first check if bucket item is not null. So if bucket item, we can add this to make this more explicit. So if this is not empty, then what do? We take bucket item is equals bucket item. I think it doesn't like the definitions being down here. Let's move them up. Right, yo. Bucket item, next item, and if this is not set, then we actually make a loop like this one just at a given start point. So we should probably move that into a function in the end. Still, just that we don't start at 0, but we start at well, bucket index would be where we are now. So we would need to increment bucket index by 1 and start at bucket index looking for the next not null entry. And of course it might be that bucket index will be incremented past that, in which case the loop will not do anything. Just that we need to remove replace m with this. So we will really make the whole thing a own protected function, which we'll call void select next. Yeah. So we might actually need to make it more. We will need to make it more complicated for the key case. So this will. We will need that select next goes here, and here instead of the loop we just use the select next function, our iterator, and we can do it because since we are the parent object, not really parent object, since we are the containing namespace, we can access the protected members. From our main function we will not be able to call select next, so it's safe and no one will mess with our iterator state except through the designated ++ operators as it is defined that it should be done. So I would rather prefer to make it. No, let's not do it. I wanted to make a return, but then we would need to make return this, and then it would not be as pretty. So let's keep it looking like this. Right here, the access to the elements, that is easy enough. Bucket item, question mark bucket item value, and we want reference on that or null. And here of this one of the reference, we are again at the situation where we kind of really cannot check anything. So we can return this, but we can first check this, then throw what do we call the error? Invalid iterator. Maybe we should write something more explicit, like iterator not pointing to a value or something, because it might, because like the end, it depends on what we define as valid. So whether we want to define a, because there are two levels of validity. One is whether it is valid in the sense that the table object it points to is still valid, because as you can see, as soon as we change something about the map, about the table, then our internal data object might get reallocated, at which point we would of course lose any validity of our previous iterators, and this is a problem, and the STL just solves this by adding additional variables and checking every time where that works. So basically we would have a pointer that points on the CX table itself and a pointer that points on the SX table, and before we do anything we would always check whether the M, or the internal data state of the SX table, of the CX table has not changed and is pointing to the same pointer for SX table which we had. And of course here that might be actually an opportunity where we might want to use one of the weak pointers which we have implemented previously. If we would want to make a very convoluted, complicated, but as safe as possible container type, we would have implemented our M as being a strong pointer, a strong smart pointer, while its reference in the iterator would be a weak pointer. Where is it? Here, somewhere there. And then we would lock it, and if we manage to lock it, we know, okay, this inner state was still valid, we can use it. It makes things on the level of what gets implemented by the compiler more complicated, but on the level of code complexity for the code that we have to write by hand, we actually reduce code. So it's often like this, that you can either write a lot of code by hand and then have as little machine code as possible, because you more or less can really optimize and only do what really is needed, at the risk of forgetting to do something important and ending up with a security vulnerability. Or you design your project such that you can write as little code by hand as possible and use different toolings that you have created, or also toolings which are provided by different frameworks, which gives you the highest level of security at the expense of some more computation. And usually how many things work nowadays with regard to these trade-offs is that memory is the cheapest thing you can get, so you never care to save memory unless you have a very special case where you would be otherwise wasting a huge amount of memory. So adding additional variables to keep track of things and add sanity checks is usually recommended. And with regard to CPU time, we still have a lot of CPU time, but it's not like memory, more or less unlimited and cheap, because the modern processors, they don't get that much faster with every year as they did 10-20 years ago. So back then, every 2 years you really had like a twice as fast CPU, while nowadays I recently got a new system, like the best you can buy for money, and it's only twice as fast as my old system from 2013. If you count per core, it has much more cores, so it's obviously much faster in this regard. Plus, it has different modern CPU extensions, which for specialized tasks gives a speed up. But if you just have normal C code that just does something without using some complex vector extensions and all these modern vector processing mechanisms of the CPU, it's just twice as fast as a almost 10-year older system. So when you write code and you cannot parallelize it, you still want to save CPU time when possible. But given, of course, the complexity of the code, the modern approach, and given also the fact that technically we have a huge amount of computation power, even in a single thread, is that you write your code without caring for the CPU time much. If you do something where you know this will be bad, then you should not do it, but you don't need to think with every line whether it will be fine or not. So an example of where one should know that it will not be good is if you, for example, have something which will have a large loop, which, let's say, has to process every element of a list, and to process this element of the list, you need to go through the whole list again. For example, in such scenarios, you know that the computational effort as when your list grows will not grow linearly, but will grow exponentially, because for it you basically multiply the size of the lists with each other again, so you have the power of 2, and this is not good. So if you do things and you work with lists of any sort, then you should avoid such design from the get-go, even if you think the list will only keep a few elements. If you know the list will never exceed, let's say, 10 elements or a fixed number, if it's really like a hard limit in your code, then it's fine, because I mean 10 times 10 is still nothing. But as soon as you have a list which can grow and its maximum size is outside of your control, you should not implement mechanisms which would be so inefficient. Then you should go to using tables, maps with binary trees. Sorted lists are a good approach, since when a list is sorted, then you can insert, let's say, if you want to insert it in an orderly way, very efficiently. You can also find elements very efficiently, assuming that you are finding by the criterion that was used to sort the list. Of course, if you sort the list by one criterion and then are looking for another one, then again you need to do a exhaustive search of the whole list, so this doesn't bring much. Anyhow, once you're done with implementing your code and only caring for the most obvious potential performance pitfalls, the modern approach is to run a performance profiler, so a piece of code similarly to a debugger which will observe your application during execution and take notes which parts of your application require how many CPU cycles. And then you can see, okay, is everything more or less equally slow, in which case it's probably fine, or is there like a certain portion, certain operation, certain function in your implementation, in your application, which is hogging all the CPU time. And then you can go, if this happens, then you can go into it and then see, okay, why is that happening? Did I do something with lists which I shouldn't have done? Is there another reason? And then you really optimize only at the targeted points where the performance profiler tells you that there is a large disparity between what this part of the application requires CPU-wise than other parts. Of course, at the end, such a application will not be as highly optimized as an application where you really would try to optimize every single line of code you wrote, but you probably will have finished with the application 10 times faster. And nowadays this is really the typical development approach. So like in the past, 20 years ago, you really tried to write your application with every line to be as efficient as possible. You also had really good performance profilers that adds to it. But nowadays, your time is more important than the CPU time. So only optimize what you know that will be a problem, or what the profiler tells you that it actually is a problem. And often these are just a few functions, a few points. So the effort really to just then revisit the functions and redo them is much less than if you would try to write every function in the most efficient way from the get-go. Okay, so having yes. Mm-hmm. Vector extensions. For the AI stuff, the NPU. Okay, so that's a good question. So technically, in a modern system which has a GPU and an NPU and a CPU, you actually have not 3 but 4 units which can do computation. Well, technically you have more, but from the programmer's viewpoint, only the 4 are relevant. You have the CPU itself, which executes logic integer operations, and it can do a floating point mathematics. We just see this as one thing, even though internally there are 2. But whether you write int or float, it's as it's like from your code point of view, you don't need to do anything special to use the other execution unit. But the CPU has also this vector extensions, SSE or AVX nowadays, and to use them, you basically need to write custom assembler code in your program, or you could also use some library which internally is written in assembler, which uses this extension. So you have hardware instructions on the CPU level which allow you to use special registers and execute these vector operations in a parallelized and thus more efficient way. So with normal x64 you can no longer write inline assembler. So you cannot write C and then write a piece of assembler and then write C again. You need to put your assembler code into some specialized assembler file which you would compile. It would expose a function which you then can call from your C code. And this way you can access this SSE and AVX extensions. To some extent, of course, it might also be that you are just using some library and it will internally really use those extensions, so you don't even, it's not really apparent to you how it is doing. For example, the very common memcopy function is often implemented this way, that it checks which extensions are available and then tries to use bigger registers for the memory copy operations. Long time ago, this was quite a significant performance improvement. And for you, as the user, it's completely transparent. You just write normal C code. Now to the other two execution units, let's say the NPU and the CPU. You cannot access them directly with that CPU instruction because it's different hardware. So what you need basically is you need a driver for the operating system which will talk to the hardware using usually just some memory mapped I/O or DMA, depending on what you are doing, and the driver then will be provided usually by the manufacturer, or in case of open source systems by the community. You can also, at least for NVIDIA, use a proprietary NVIDIA provided driver, and the only thing you can basically do is you can, from your C application, talk to the driver. And usually, since the driver will have some probably also rather convoluted API, they will provide you a own library which you then can include into your project, and then you just call functions on that library, and these functions will then put instructions, put some code into the usually those additional units like a GPU, CPU are called accelerators because they accelerate specific operations, while the CPU is the generic thing and can do anything. So basically, if you, for example, have an NVIDIA graphics card, you would use the CUDA framework, which provides you the needed drivers, the needed libraries, so that you can write a code for the GPU. And it can also, I have not used CUDA myself, but given the flexibility of modern GPUs, I wouldn't be surprised if it would also allow you to write, not just like make simple calls that you can use to tell it one thing to do, but where you could really write some code in some specific language which is optimized for this particular accelerator, and then this would be compiled with a compiler provided by the manufacturer to a binary representation, giving you a blob which you can then, using the API through the library, feed into the let's say into the GPU or the NPU. So this would be the workflow. So as you see, it's quite significantly more complicated and requires additional tooling. So for example, just with Visual Studio, you could not compile any blobs that you would then feed into the GPU or the NPU. You could use the API and the libraries which you can just include into your C project to feed it existing blobs. So for example, if you would only want to load an LLM, which you just download already pre-trained from the internet, into existing NPU, you could probably do it without any additional tooling. You would only need the right library and the right driver. But as soon as you would want to write some own CUDA code to compute hash functions, like for example it's done for Ethereum mining or such things, then you would already need some compiler from the CUDA what's the name, framework, so that you can really write basically a program which will run on this individual GPU cores. And usually I would expect it not to really be something that you could write just in C, because C is really more meant about operations on single variables, while everything about the GPU, for example, is about operations, like making many operations of the same sort, so vector operations basically. So it would probably be a more declarative language which is more similar to something where you describe a hardware than something where you really like write ifs and loops and stuff like that. I don't think as a GPU would like loops and especially branching like ifs, because this would always mean that you cannot rely on pipelining so much. And this is, however, one of the things that makes modern CPUs so fast, or generally modern processing units, that you can just pipeline many steps of an operation one after the other, and then you can like basically execute 10 instructions at the same time, just for each instruction a different portion. So if you are piping in like 100 instructions, that will be as fast as if you would have piped in probably like 30, because you need like the first things which get piped in don't benefit because the next stages are empty, and the last thing that comes out also, but the stuff in the middle gets really nicely overlaid. So you really require something where you really prepare the data and feed the data and they are processed, but don't make decisions while you do the data processing. And of course, C and C++ is not suitable to this. You can of course program such things, especially if you would want to use this vector extensions of the CPU itself. But if you are making like a language for a completely different hardware which is optimized for such pipelining and parallel processing, then I would assume that you would from the get-go just design the language itself completely different. And since you need to compile it with a completely different compiler, there is no benefit in reusing something existing. But as mentioned, I have not used CUDA myself, so I have no first-hand experience on how this works in detail. Yeah, you're welcome. Okay, so where were we? Right, we have here our dingens. So actually we could already be able to go through a list, a table. Let's try it out if I did not forgot something. So we have here the table. We insert many things. So make for auto e is equals my table begin is over my table end plus e. That's more efficient of the two. Okay, doesn't like that. Why? This is public. Here, this one should also be public, and we have a default constructor and assignment constructor. They say it. Did we forget the copy constructor? I don't think we did. This should be const. Sorry, both const. Okay. Right, and now we just, let's say we will print f % s. And what's what? First the key %del %s \n comma e. That's of course also something. We also want to get the key. You need the other function to get the key. Around those operations. Okay, reference. Did I use capital K or not? Okay. Let's just return something. Actually, I could make the other ones also const. Doesn't matter. Let's keep this whole optimizations for later. Wait, it's also a bug. That should be just value. And here we just take like something again, bucket item. But we have bucket item has key, so that should be fine. Right, so we take the key and we print the thing. Okay, let's wait, s, that's not correct, because s gives us a string, and on this we need c star. If we take asterisk I, that should give us, where's our asterisk operator? Yes, undefined, we I have broken something. Let's see what the compiler says. What's the first error that pops out? Like this, but it should be able to access the t of the. Oh, it's not. We don't have t. It's called the phi for value. That explains it. V and k in, not t. Okay, and other should be capitalized. Right, and here we are on ourselves, so we don't use the capital I. We have get PTR. Oh, we don't have get PTR. We rename it. Create, resize, insert. It was find PTR. So wir können den Protected Member hier nicht zugreifen, dann müssen wir das. Sorry, if it doesn't want to let us access it, then we will need to define it explicitly as. I thought if it's an object which contains it, it should be freed automatically, but apparently not. Right, that should be dots. Here as well. As you see, when using templates, the compiler finds all the bugs only later on once the things are used, and not instantly as one might want. Good, so this works. Let's see if we get the right result. We do not. Bucket item. It did something, I did nothing. It failed on the very first attempt. So bucket item will probably be invalid. And no, it doesn't look invalid. Value. Oh, that's a mistake. It should be if this does not exist, then throw an exception. Okay, now it's fine, but why did we try to dereference something that does not exist? Okay, so it printed out probably all the items, so the is not end failed us, apparently. Oh yeah, of course, because we checked all the things and the end only is defined for the bucket items, so we just dropped the. No, we should not drop the index. We need to set the bucket index to something defined when we run out of entries. So if this thing fails, then basically the next is then the empty, so bucket index should return to 0. And bucket item will be set to null PTR, because before it wasn't, and this ensures that the comparison will be right. Yep, we didn't crash, we proceeded past our printout. So this works as expected. Let's put a breakpoint here. cute. That's that. So now we need to improve this such as to be able to handle the find function. So we want to implement this find thingy, and we will start, and we can copy this part for beginners. Since if there is nothing, then it will be empty anyways. And then let's see how we do that. We will use the find ptr, but no, that's not good because there we don't return all the values. I mean, we can calculate this. Then we just need to look for the key, and then it will give us the right thing. We will need to hash it twice. That's slightly less than performant, but it saves us a lot of code, so I guess this will be the best approach. Or we could also change this find ptr slightly. That's, I think, the best option. Let's just we will add it an ability to retrieve the index on success. Right, return entry if key matches. If index is index. Oops. Nice. This sounds like the most efficient approach. I mean, efficient is relative because now you always check whether this parameter is null, but this is a very fast operation. So, given that it gives us a much more elegant code and avoids complications, I think this is a good approach also. Oops, we will do this first. We'll do this slightly different. We'll do this first, and if this is null, then we just return end because there is nothing, and we need we want to get the index. Okay, so me punct bucket index is index, and e punct bucket item is equals what we found. I mean, we could optimize this actually even more when I think about it. If we put this here and that there, then we don't need this because it pretty much does the same thing. It creates a thing, it assigns m. It tries to find, which checks whether m exists, and if it doesn't find it, returns null. This is null anyways, this will be assigned, so that's already the whole implementation of find, with the one restriction that the next operator will not allow us to go to the next with the same key, but to the just next in the bucket, which is not necessarily what we want. So here the print out, we can put a breakpoint here, and then auto f is equals my table find, let's say 50, and then of course we need to check whether we found it. If find is ungleich end, then we print it. Else we print not found. Let's try with something which should not be found. First, yeah, not found. Now let's try with 50. It's still not found. Not good. Oh wait, we divide by 3, so we don't have a 50. Let's go with 20. Good. 20, 62. Well, we should have 3 of those entries. Actually, I can just run it further. Why didn't we print anything now? That's because it didn't apply the changes. Now it should have printed. No? Huh. Interesting. We start here. Begin. Select next. Bucket index. Okay, select next is failing. Let's see why. Bucket index table bucket count. Bucket index is 0, bucket count is 80, table. Okay. This is not null. Okay, but it assigned those values correctly. Is our copy constructor wrong? Bucket index, bucket item, that should be fine. Okay, let's. Oh. Let's investigate that. So we start with our for loop. We assign something, we break out. Yeah, and we should return instead of breaking. Because if we just break out, we always execute this and set everything to 0. So this obviously is not what we want. But if we return, then it will be fine. Then it will print everything. So we found at the key 2062. Now let's look for the keys. And we have 60, 61, and 62 as keys. So our next goal will be to find a way to iterate through all the entries with the same key. Once we found something, so we will pretty much just copy this, or maybe even better, we just only copy one line, and from this we do a find 20. And this will mean that we will need to change the behavior such that it checks the keys when iterating through the bucket. Normally, I think in the way STL handles it, you would not have this behavior. So in STL, find will give you the first valid entry, but if you then ++, it will just give you the normal ++ behavior as we have now. So you would then need to ++ till pretty much the end, because you don't know when the bucket ends. Generally, this behavior is much more elegant with sorted containers, because if you are using a std map, so a sorted tree, then if you find, it gives you the first entry, then you ++ on it, and since it is sorted through the normal ++ behavior without even a key test, it will give you the next at the same key, the next at the same key, and at some point it will give you an entry with a different key, but then you know that there are no more entries with the key that you were looking for. So at this point you can break out from the loop. I might implement a quick test demo case for that later on, because it's quite a nice behavior. But as said, it only works with sorted containers. And here we want to make our container better than the STL, so we will add this new behavior. And I think the simplest will be to add a variable. Well, we can do it 2 ways. We could either use a pointer that will point to the key, to the first found key, and then just demand the key to be the same, or use a boolean, and then we will reuse the key from the previous item. The more fail-safe option would be to use a boolean, but since we can expect the pointers to get the iterators to get invalidated whenever we do anything to the data structure, the underlying data structure, technically a pointer is not that much worse. It just gives you more opportunity for it to not work correctly. So let's see, key asterisk key is gleich ptr. Okay, and if we are here in this this method, what we'll do now is what's that find here? The find. So if this, then e punct. I use already key for the function. Then let's call it filter key. E filter key is equals Referenz bucket item error key. That should be the right thing. It should work. Yeah, just checking that because the IntelliSense again didn't show us anything. So if we are here and this is not null, because I mean if the bucket is out of entries or is empty, then we don't have anything to do because it won't be in the next bucket or anything. So if let's make this to the next bucket item if filter key while it's while bucket item and bucket item key is not equals asterisk is not equals filter key, then bucket item is equals bucket item p next, and then here we need to check if bucket item then return else fall through to this case. Can I improve that? We can make this we can move those two up. Okay. We can. So we assign the next item. It might be null. We check if we have a filter key. The filter key always checks this value anyways. Then it does the comparison only if. Wait, that should not be. That should be just filter key. And we can make it explicit. So if we have filter key, and while we have a bucket item, that looks nice. Let's keep it like this. And we have a bucket item, and the key is not the same. Then we go to the next bucket item until we either find the right key. Find the right entry with the key or run out of bucket items to this will not be great. This will not be great. First of all, we don't want this in the select next function. We want that behavior in the ++ iterator. So let's if I just select next, it would be nice if we could use the ++ iterator for this. But we cannot. Okay, well, then let's change this. Let's undo these changes here. I have a copy of the function for later. But then this will be not select next, but this will be then called just select first. But we use it here. It would be nice to make one function that does both. Bucket index. and we could just call it select next bucket, or from next bucket, because then it is clear, then it just goes to the next bucket and nothing else. I don't like it. I would like to combine those two, but the behavior is a bit fundamentally different, because the thing in one case we kind of want to find the first thing which we start off with, while with the second case we kind of want to increment past the first element which we have right now. Let's keep this as select next, because what we will never do is we will never select from the next bucket if we are in the plus plus operator for the key. So let's make it like this. If filter key else. If filter key, well, we always need to check the if there is the item, if there is the next item, because if there is none, then we don't have anything to do. Okay, so we have the filter key, and we know we have a bucket. Now we make the loop. They keep this, yeah, kept it, this loop. Alright, so we have a bucket, we have a filter key, we have this, and then we go to the next bucket, and if this fails, then we need to set the index to null. Well, not in, but only in the uppercase. Yeah, that's good enough. That should do it. So find 20 and let's run. Filter key, capital K. And it gave us all the right 3 entries. Nice. Okay, table. Good. So this works. I'm thinking whether we want to somehow make this more elegant. Because it would be, yeah, but this is good enough. Just the name is not quite nice. We just call it next bucket. It's like select next, but it's more clear that it tries to find the next bucket, including the current one we are right now in. That is good enough. Okay, so the iterators are done. Let's see what else we would want to do. Do we have any to do? So we have the homework. Do we have any other homework around this container? Yes, we can add this exotic insertion mechanism. Homework from the, what's today? 12. Insert. It would be nice to use here an int then we can use different things. So this would be 0, 1, 2. Then we add a insert bottom. Or just append, but because the default behavior, normal replace and duplicate, comma append, and the other will be append, and this will be 0, 1, 2, 4 is good. So we can here provide a list of options. Mode. We'll use the end to test this selection, so that we can then check for the insert keys. Or append is equals. Oops. So you can use the end operator to very efficiently test for single bit flags, because that's like the normal behavior. It's like just null. That's like first bit set, second bit set, third bit set. We could of course have both of those set, which would be inconsistent with what we want here, but oh, actually actually this is not correct. This must be null, or just exclamation mark this. Right, so if multi is not set, no, yeah, if multi is not set, then we do this. If multi is set, then we do that. And if we do this, we either, if we don't find it, we still do that, and then the rest works. And if this is set, then return. Yeah, now it's fine. Okay, now, and the append is set if the append flag is specified, so we would pretty much call it like insert, comma, you need the whole type, that's semi nice, multi append. This is terrible. We should define the flags outside of the template. Because that's terrible otherwise. AX table insert mode. And there should be an enum class so that we are bound to the namespace, which complicates things a lot, because you cannot or those things without casting them to an integer. Let's keep it inside. It's ugly, but it's confined. Otherwise, we would need to get these names such that they are globally unique, and although we could put the whole thing in a namespace. There are ways, but let's keep it simple. Right, and then we would pass this to that. Insert ptr. And the append is the thing which then you will need to, then we have insert entry and so on. So from this point the homework starts, and there is no here, yeah. So maybe I should actually move the homework indicator downstairs. Homework. For the append flag, add support for the append flag. when the append is true, the new entry be added to the bottom of the bucket instead of being in at the top. Yeah, it's not super difficult of a homework, but I don't really have a good idea for what you could do with this yourself that wouldn't be completely contrived, because this is a useful use case, because you might want to maintain the order of insertion, and this ensures this, because we also have this improved iterator, so we can basically what this thing does now is like if we would have a x tree and as the value an x table, but as the value have a x list to which we then would be able to append things. Although there is one more thing that one could think about. That's a good exercise. Let's add a second homework. This one was really too simple, so 1 and 2. Add support for iterating the other way around. So add add a minus operator to the note. This will require the to be changed from a single linked list to a linked list. That's a nice exercise. It adds some additional memory usage. Not fine. Int. I want to store a tail array in M to the int optional, comma. You may want to store a tail array in M in addition. We should not write M, we should write the name of the object. SX table. In SX table in addition, comma, in order to improve the performance of appending. So if you do 2, then actually we should just change the order of those things, because the naive way of doing now 2 would be to just go through the bucket until you find the end and then inserting it, which if the buckets don't have too many entries is fine. But if you do this anyways and we want a bidirectional one, you can have a second array of the tails, and then add append will be just as fast as add prepend, like the default one. Right, and we have 9 more minutes, so I will quickly show you how the STL thing is handled. That STL map. STL map, and we also should use a map string in this example. Map std string std map insert. And the first thing that's annoying about the map is that it doesn't have a nice insert function, but as you see here it takes many different annoying things, and the way to do it properly is std mk make pair key is the first argument, so let's say 1, and the value for the string is the second argument. So the inserting the STL way of inserting into a map is annoying, because with other containers it's trivial, because you just append whatever type you have. But the map, since it kind of holds tuples of key and value, it wants you also to provide an already pre-made tuple instead of making it. Qt is much nicer. Qt allows you to just insert value, key comma value, and they should have added such a convenience function. At least in the old, actually I should check whether it might have been added in one of the very newest C revisions, but in the older C, and I think even in C11 this was not present. And yeah, should use a loop as well to insert things. Alright, and we wanted to have multiple at the same one, so we don't need a map, but a multi-map. And in STL you also have like a different type for a map. In Qt the same, you have map and multi-map, although they are on the backend the same thing, just that they are parameterized differently, at least in Qt. In STL I haven't looked inside. Alright, so we take I and our string as the value. And pretty much we can just copy this here. std map, find 10, find 20, but here the behavior is differently. The key is first. And the value is called second dot cstring. And Qt uses again a different notation. Qt uses, if I recall correctly, dot key and dot value, and value and keys are functions, so they need brackets. So it's really made like some things are standardized, like begin and end, and iterated that it needs a plus function for the range loops, but many other things about how the iterators work are individual for every framework. Everyone cooks their own flavor, what they prefer. So I'm actually not sure if Qt does not provide. No, they don't. The most annoying thing is that if you would like to have capitalized first letters, and then you want your object to work with the range loops, that you need the, or was it here somewhere, the small lowercase begin and end. Right, okay, we have this. Right, we start at here, but now the iterator will start at 20 and it will run till the end, so we can take a look on that. What did I forgot? Didn't we use that? Did we bring? Oh, the semicolon is missing. Right, so it starts at 20 and then it keeps wait, we should not insert I, we should insert K. Oops. There. We should put a breakpoint here though, that we don't run too far. Right. So now starts at 20 and we have the 3, and then we get the next and the next and next. They're sorted, but we are keep going past kind of the end of whatever key we wanted. So what I always do if I want to use a multi-map like this, I just check if this first is still equal 20. It shouldn't actually make it nice. Int key. It's really how I do it. I have a variable that holds the key. I get the first iterator because the find will always give you the first, and if you plus through it, you will always get then the next ones until you get one where the key is not first. The key is not what's inside, and then you break out, and then it behaves the same way. That is not expected. Wait, what? First, like key. How was it? Sorry. It didn't. It just printed garbage. It works as it should. So as you see, it ends when it ends, and since it's sorted, it knows that nothing else would come. If we would, however, use a unsorted there. Okay, we need to include that. I think it was unordered, not unsorted. So let's comment this out. Unordered multimap. Yes. And then we will comment out only this line and remove the test here. And if the name does what it should, then but it was wait, why was it still ordered? It should not be ordered. It might end up ordered because the key funny. As it happens randomly, the way it's implemented internally will maintain our order. I mean, the thing is, we are of course inserting in order. That might be a reason why this behaves this way. We could of course change this to insert at a random key. Keys random modulo. Let's say we want up to 30, or even less. Let's go up to 20. But then we need to change this to 10 or so. Okay. Let's see. 10. And now it just ended up at the very end, which is interesting. Let's look for 5. Okay, now it is not ordered. So apparently we ran into a edge case where the hash function aligned with the inner logic of the instrument, that in this case it ended up to be ordered. But now, since we changed it slightly, we see this ordered behavior, although it still keeps the keys adjacent to each other, which is interesting. I was not aware that it would do that, because this actually adds complexity. Or it really has so many buckets that every key ends up in a single bucket. That can also be. So that is still kind of random that it is grouped. In which case it would, however, mean that if we it tries to keep it that, well, one would need to take a deeper dive into it, and we don't have time for that because it's a hugely huge class. As you see, the whole file is 2000 lines, so it seems that however they implemented it, it at least keeps. So either it has a really good hash function such that we really get 1 bucket per key. We could test this if we really would generate some very, if we would, for example, use strings for keys and use very long random strings, then we could try to find out how well this works. But unless they wrote that somewhere in the specifications, which one would need to find and check. So unless that's the case, I would not rely on this being correct, because it's called an unordered map for a good reason. And in the past, it was actually just called a std hash, because internally it should be a hash table. They also might have changed the implementation internally from, but no, I don't think so, since if you go on this, you see that this is already derived from a sorry, now that I clicked on the map. The map is derived, as you saw, from a tree, and the unordered map is derived from a hash something. So it will be a hash table on the back end, so it must be unpredictable for some scenarios. But as said, it's probably just that they have a really good hash function, and we just end up with whatever we choose as values to them being spread into different buckets. But at the same time, it would mean if we would use much more values, we might have a good chance of finding a collision, a hash collision. But since we are out of time, I think it's the time to finish. We'll see each other in a few hours for the main lecture. And that's it. See you later. Bye bye.